Hi, grade 11. In this video, we talk more about the quantum numbers. In the last video, we talked in details about the principal quantum number. Now we move for another quantum number. Okay, the other quantum number we are going to talk about today is the subsidiary quantum number. What is the subsidiary quantum number? We use it to identify the number of sublevels in each energy level. It carries the symbol L, small, okay? Identifies the number of sublevels in each energy level. How do we identify the subsidiary quantum number? Actually, we have this symbol rule, L equals n minus 1. What is n? N is the principal quantum number. Okay, let's try to know how many sublevels exist in the first energy level. So we apply the rule. L equals n minus 1. 1, the first energy level, minus 1 equals 0. This is a single value, one value only. If I have one value only, this means that I have one energy sublevel, which is the S sublevel. The S sublevel is carrying a subsidiary quantum number equals 0. Let's see another example. Let's talk about how many sublevels in the second energy level. Again, we apply the rule L equals n minus 1. N, second energy level, then n equals 2 minus 1 equals 1. This is not a single value, actually two values, 0 and 1. If I have two values, 0 and 1, then I have two sublevels in the second energy level, S and P. As we said in the previous slide, S carries the L equals 0, then P carries the L equals 1. The third energy level, again the same rule, L equals n minus 1. This is the third energy level, so n equals 3. 3 minus 1 equals 2. Again, this is not a single value. This is a range of values. 0, 1, and 2. I always start from 0. So 0, 1, and 2. I have three values. This means that I have three energy sublevels, SP, and this time D. S carries value 0, P carries subsidiary number 1, and D carries 2. The last one is the fourth energy level, L equals n minus 1. 4 minus 1, this is the fourth energy level. The answer to the equation is 3. The 3 here is not a single value, it's a range of values from 0 to 3. This means 0, 1, 2, and 3. I have 4 values. Then I have 4 energy sublevels, S, P, D, and F. The S for the 0, the 0 for the S, 1 for P, 2 for D, and 3 for F. Okay, what about the rest of the energy levels? The 5th, the 6th, and the 7th. Actually, they all carry the same 4 sublevels. No more. S, P, D, and F. Okay. Let's talk about the magnetic quantum number. Actually, this number, the magnetic quantum number, helps us to identify how many orbitals in each sublevel. The orbital is like a room or a space at which the electron exists or rotates. Okay, so how do I calculate it? The magnetic quantum number carries the symbol ML. Okay, this is ML. And it equals 0 in the middle, again it's a range of values, and I keep moving until I reach positive L if I move to the right, or I move to the left until I reach negative L. Let's take an example, and we will start with the S sublevel. The S sublevel has a subsidiary quantum number equals L, and the L equals 0. So I have nothing else, it's only 0, so there is no other value to take its positive or negative range. So ML in this case for S equals 0. But in the P sublevel, we can find it in a much clearer way. The P sublevel has L quantum number equals 1. So 0 in the middle, and I move to the right until I reach positive L, which is positive 1 in this case, and I move to the left until I reach negative L, which is negative 1 in this case. How many values do I have here? I have 3 values. 0 in the middle, positive 1 to the right, and negative 1 to the left. This means that the p sublevel has 3 orbitals. Take a look at the picture. Each orbital has its own magnetic quantum number. This magnetic quantum number for this orbital 0, for this one is positive 1, and for this one is negative 1. And we know from before that each orbital can be saturated up to 2 electrons. So the p sublevel can take up to 6 electrons. Another example, we are going to calculate how many orbitals in the D, for example, sublevel, the sublevel D. So the D is carrying a quantum number L equals 2. So again, 0 in the middle, like this, and you move to the right until you reach this positive value. So it's 0, positive 1, and positive 2. Then to the left until you reach the negative of this value. So it's 0, negative 1, and negative 2. Calculate how many values do you have here. You will find 5 values. This means that the d orbital has the d sublevel has 5 orbitals, like this one. The one in the middle is carrying the number 0, ML0, magnetic quantum number 0. This one positive 1, this one positive 2, and from the left, this one negative 1, and this one negative 2. Again, how many electrons can I find in the d sublevel? I can find 10 electrons, since I have 5 orbitals, and each orbital is carrying up to 2 electrons only. Okay, let's see another orbital, or another sublevel, which is the f sublevel. Okay, the f is carrying a subsidiary quantum number equals 3. So 0 in the middle, and move to the right until you reach positive L. So 0, positive 1, positive 2, and positive 3. This is from the right. From the left, I need to reach negative 3, negative the value, negative L. So it's negative 2, negative 1, negative 2, and negative 3. How many values can you count here? You can count 7 values. 1, 2, 3, 4, 5, 6, and 7. This means that the F sublevel has 7 orbitals. These are the 7 orbitals. The one in the middle with 0, then positive 1, positive 2, positive 3, and negative 1, negative 2, and negative 3. 7 orbitals with 14 electrons. Now for the last one, which is the spin quantum number. Each orbital is like a room that can take 2 electrons only. Okay, the first electron always, as the world agreed, is entering this orbital represented by an arrow with heads up. Okay, and if the arrow is with head up, then it means that the arrow is going to rotate clockwise. The other electron is not entering the orbital with the same direction of rotation. Actually, it enters like an arrow heads down, and it rotates anti-clockwise. And why is that? Actually, if I have 2 electrons in such a tiny space, and the 2 electrons are both carrying a negative charge, then they will repel. But by the difference or making difference in the direction of rotation, one of them is rotating clockwise and the other one is rotating anti-clockwise. This is going to decrease the repulsion force between them. Okay, let's take a look at this picture. This is the first electron entering, and this is the second electron entering in the same orbital. Now we are going to insert another 2 electrons in the second orbital. This is the first one. I cannot put the second one like this because it means that they both are rotating in the same direction, and this is wrong. One of them is rotating clockwise, arrow with its head up, and the other one is rotating anti-clockwise, and I will know that by arrow heads down. Okay, if the arrow is rotating clockwise, this means that its spin quantum number equals positive half, and if the arrow or the electron is rotating anti-clockwise, then the spin quantum number equals negative half. Okay, now let's talk a little bit about how to insert electrons in these different orbitals and sublevels. If I need to insert electrons, I need to follow specific rules, and the first rule is the Aufbau principle. And what Aufbau is saying is that electrons are going to fill lower energy orbitals first, then they are moving to the higher energy orbitals later. Okay, the Aufbau principle is also called the building up principle. Okay, let's see this. This is telling me, this picture is telling me which orbitals are with lower energy and which orbitals are with higher energy, or which sublevels with lower energy and which sublevels are with higher energy. So the 1s is the first one, the 1s. So electrons are going to fill the 1s first, then the 2s, a little bit higher in energy than 1s, then 2b, then the 3s, then 3p, then the 4s, then 3d, 4b, and 5s, and so on, like this one. Of course, in the old curriculum, you would have to memorize all this, but now since you are going into exam with open book, you do not need to memorize. With time and with a lot of exercise, you will be able to tell which sub-level is with higher energy or with lower energy. Just one note, 1s, this is the S sublevel that exists in the first energy level. So this one refers to the number of the main energy level or the principal energy level. Now I have 2s and 2p. These two sublevels exist in the second energy level. So this 2 and 2 means n, the principal quantum number, equals 2. Now the third energy level. According to our knowledge, in the third energy level, I should be able to find 3 sublevels, S, P, and D. Okay, here is the S, 3S, and the 3P, but I cannot find 3D. Wait, this is 4S and this is 3D. This one should be here. Why is it coming after the 4S? Actually, because the 4S has a lower energy than the 3D. So practically, the 3D exists exactly where it should be. It exists in the third energy level. 3D exists in the third energy level, but the electrons fill the 4s first before they go and fill the electrons in the 3D, and so on. The second rule that I should be following to write the correct electronic distribution is another rule that's called Horn's rule. And Horn's rule states that every orbital in a subshell is singly occupied first with one electron before any other electron is doubly occupied. And what do I mean by that? Let's take the 1s. I get one electron, then the second one. Okay, I can have only 2 electrons in the 1s, and the 2s are the same. But I have 3 electrons in the p sublevel. Okay, so I cannot put 2 electrons in the first orbital and 1 electron in the second orbital and leave the third orbital empty. What's really happening is that electrons are going singly first. So 3 electrons in the p sublevel means that I have 1 electron in the first orbital, the second electron in the second orbital, and the third electrons in the third orbital. If I have 4 electrons, like in the case of nitrogen, 4 electrons in the p sublevel, then one electron, the second, the third, and then I start all over again from the first orbital, and I start to insert the second electron, like this one. Okay? We need to take more examples about the electronic distribution, and this is for the next video, inshallah. Okay, thank you so much, and see you soon.